We shall resume. Well, I really feel like I'm doing a media interview here. We've got four cameras. This is unusual. Plus all the secret ones that the government has in here, right? So, yeah. Yeah. And there. Yeah. That's right. Yeah. Well. Fortunately, none of this is very secret. In fact, the struggle is to get anyone to pay attention to it. So, yeah. I mean, who knows? Maybe the government people watching the secret videos will become interested in AGI, and it'll be a good thing. Yeah. So back to where we were, and still going through sort of the high-level overview of OpenCog and how it works. So. I had talked about these different learning algorithms and how they all interact with the atom space. And now, each of these algorithms is really a story unto itself. And I'll talk more about some of them than others during these couple days. I mean, there's a bunch of time, so I think there is time to go into each of these in some depth. But I mean, so PLN, probabilistic logic networks, is fairly analogous to Pays-Nars logic, actually. I mean, it's in the context of OpenCog as a whole, we're not trying to use it to do everything, but I mean, you could. Like you could say, well, PLN is the ultimate core logic of intelligence, and try to build everything on that, and that'll be quite analogous to what Pei is doing with NARS. And so, as a kind of framework for reasoning, PLN is pretty well articulated. Now, as a code base, so far there have been two partial implementations of PLN written in the OpenCog framework, each with different problems. And right now, the C++ one hasn't been used for a long time. It might still work, but no one's tried to use it for a number of years. The Python version that Jade O'Neill, formerly known as Jared Wigmore, wrote, works for small atom spaces, basically, and it doesn't scale to large atom spaces, and it works through a kind of flaky special PLN Python shell that Jade built, which is separate from the scheme shell. But that is possible to use, and has been used for kind of testing and prototyping various things in PLN. Now, a guy in Isfahan, Iran, named Ramin Barati, is now building a new version of PLN, and he is finally doing it according to my own desires, which was not the case with the previous two versions. I mean, OpenCog, while I founded the thing, it's a fairly heterogeneous project. So, I mean, if someone is a PhD student or something working on implementing something, it's not necessarily going to be done in accordance with my own cosmic master plan. And sometimes that is for the better, because other people have ideas that I thought at first were bad and ultimately turned out to be good. Sometimes it's for the worse, and someone winds up getting into a dead end that I would have foreseen. And in the case of PLN, the way I want to do it is more strange than a typical logic engine, because I wanted to basically use OpenCog's attention allocation for inference control. So you break it down like an individual reasoning step, like the familiar deduction, induction, and abduction or something. And an individual reasoning step is one thing, but then how do you coordinate which reasoning steps to do? So I've worked out a way that I think you can use the attention allocation, the spread of short and long-term importance through the system, to basically choose which reasoning steps to do. So based on the reasoning steps that you've done before, the things that have led to interesting conclusions get more short-term importance. That short-term importance spreads through the network, And then the more important things are more likely to get chosen for the next reasoning steps. And there's more detail to that, which I can go through. But the idea there is in line with the whole cognitive synergy perspective in OpenCog. But I think logical inference engines on their own are not going to scale up for AGI because inference control is hard. And you need something else besides kind of ad hoc control heuristics. And I think Pei realizes that. He has various sorts of chunking and so on that he tries to use for inference control. And the idea here is to use the attention allocation, which is sort of the nonlinear spreading of importance among the neurons, the sub-symbolic aspect of the network, to guide inference. And I'll talk about that later. So that's about inference control. Now, in terms of the actual logic, what I did with PLN is in concept pretty simple. It just took a pretty powerful logic, which is aspects of term logic and predicate logic, and just make it so if you attach probability values to the premises of an inference, you get probability values out in the conclusions for the inference. So make it so you can do logic but propagate probabilities through the logic. And there are a bunch of other people working on stuff like that. Every year in Europe, there's conferences called Probability and Logic. And so there's a lot of people doing math about how you put probability and logic together. And in PLM, we've done that in a particular way, which is different than what the people in the project community have done, because most of them are pure academics oriented toward proving things about very special cases. And what we were trying to do is make it work for an entire complex logic system to be able to propagate probabilities through it, even if we had to put some heuristics in this or that place to make the whole thing work. And so obviously there's a lot of story underlying that, which I'll talk about a little later. And with the C++ version, we used it for some things. I mean, we used language processing to extract relationships from biomedical research abstracts, and then derive some conclusions from that with logical reasoning. And we did some proprietary things for a U.S. government agency with doing reasoning on analyst reports and so forth. So most of the work there was connecting some language processing software to PLN and having it draw conclusions. And that's fairly narrow AI-ish, really. It's special applications, but it was using the same PLN logic. And we also used PLN at one point for agent control to make a video game character in the crystal space game world learn to walk around and find things and so forth, which that infrastructure has long been in disarray because we haven't used the crystal space world or any of that for a long time. But it should be possible to get that sort of stuff working then in the new Unity 3D world that we're working with.
Did it work?
What?
Did it work?
Yeah.
You walked around and got stuff?
Yeah, it worked.
Cool.
It worked. I mean, it worked to the level that academics need something to work. We ran a demo and we wrote a paper, and it was all genuine. Did it work robustly? Probably not. Meaning that if you varied the environment and varied the task in a whole bunch of natural seeming ways, would have still done it without requiring tinkering of parameters or something? I doubt it, to be honest. So, that's one thing you find when trying to make a system actually do something is getting it to work well enough to give a demo and write a paper is a very different thing than getting it to actually work.
A quick question. What's the main difference between this network and the Bayesian network?
The closest analog in the Bayes network would be a Markov logic network. Because a Markov logic network, that's a richer logic representation language than a Bayesian network. Because a Bayesian network is just estimating a conditional probability. Yeah. So whereas here we deal with existential and universal quantifiers and Skolem functions and the whole apparatus of mathematical logic. Now, Markov logic networks are not really that thorough either, because in a Markov logic network, you basically Skolemize out all bound variables from the existential quantifiers to get a simple network with only universal quantifiers. And that works for some applications. But ultimately, if you're trying to reason on knowledge from natural language or something, it's a very awkward representation. So the main difference is that in Bayes nets, and even in Markov logic nets, they use a simplified representation in order to make reasoning faster and scalable, whereas here we use the full, just complex logic representation. And the result is that either it's very slow, or you need to control very closely what inferences you do. Because like in the Markov logic network, you kind of, inferences are going everywhere until it relaxes into a steady state. And if you did that with a more complex logic, it would take forever. But yeah, the other difference in practice is our truth value representation. So we don't use a single probability truth value, we use an imprecise probability. So it's a little bit like what Pei does, because he has a strength and confidence, but what we do is probabilistic. So, I mean, instead of a strength and confidence, you can look at the simplest imprecise probability is of the form lower bound, upper bound. So it's just an interval probability. And you can look at various more complex versions, like, say, you could look at, say, a probability that's 95%, it's 95% likely to lie in that interval, right? Then that's an imprecise probability, and that's the analog within probability of Pei's two-component truth values. But the advantage of using this sort of imprecise probability is that you can then use all the math of probability theory instead of having to make up your own mathematics. Right? So, yeah, the difference is the logic is of richer representation ability, and we use imprecise probabilities. Then there's other various peculiar things we've done in PLN. So Pei had his distinction between extension and intention in logic. And we deal with intentional inference in a particular way within PLN, which is different than Pei's way. But that's a peculiarity of this particular logic underlying PLN. So we look at extension, just like Pei has extensional and intentional inheritance. We have extensional inheritance, which means inheritance of members. Like is say, cat inherits from animal, yes, because the cats are also animals. Does whale inherit from fish? No, because the members of whale are not members of fish. On the other hand, if you look at intentional inheritance, are the properties of whales also properties of fish? Many properties of whale are properties of fish. So you could say there's an intentional inheritance between whales and fish. But what we do is we define what does it mean for one thing to be a property of another. And you can use mutual information for that. For example, how much information does this give about that thing? So the fact that a whale swims in the water gives you some information about a whale. So if you define what it means for one thing to be a property of another using mutual information, you can then define intentional inheritance as inheritance of the set of properties of something. And that's one component of PLN. So actually, yeah, Pei and I worked together from like 98 through 2001. So when I left, I was an academic from like 89 till 89 till 96. Then I got bored with that and got the insane idea to start an AI company. And Pei was one of my first employees. And so at that point, I learned all about his wacky NARS logic and so forth. And we had, then in our AI system at that time, which was the WebMind AI engine, we had a NARS implementation, and we had an implementation of some precursor of PLN. And then we test them together on different problems and so forth. And then eventually that .com company ran out of money, and then Pei and I went off to do different things. Right? The way we were testing those systems, NARS often came up with nonsensical results. However, he might say we were not testing it the correct way. So he's not here today. Right?
It's great to hear the voice in the back of the room saying, "Oi."
We've argued this a lot. Yeah, I mean, I think his induction and abduction truth value formulas don't work very well. But
I was wondering about this, like whether when they do the inference, if we put loads of data to test it, whether the confidence level will converge or it would be completely...
Well, I mean, of course, he's thought about this stuff a lot, and what he thinks is the simple examples don't showcase his system properly. That would make sense in the large scale when you do a lot of different, when you're doing millions of inferences or something. So. So I mean, a simple example of how the difference between NARS and the probability system comes out of, if you're doing an inference like, okay, Ben is an AGI researcher, some mystery guy X is an AGI researcher, what's the chance that X is actually Ben, right? Now, if you do that using a system that interprets these as conditional probabilities in some way, then the answer will depend a lot on how many AGI researchers there are in the world. Like if there's 3 AGI researchers in the world, these odds are fairly high. If there's 10 million AGI researchers in the world, then from the fact that both Ben and X are AGI researchers, then the inference that Ben is X is very, very weak, right? So in PLN, or any system that treats implication as a kind of conditional probability, then this conclusion is going to depend not only on the strength of this and this, but also on basically the node probability of that. Like how likely is it that someone is an AGI researcher in the first place, right? So in PLN, because it's based on probability theory, not only the links, but the nodes in the network have probabilities. So not only the relationships, but the terms have probabilities. And in NARS logic, there are no term probabilities. There are only link probabilities. So how does Pei not get a wrong answer here? Well, he says you have extra knowledge put into the system saying, well, there are only a few AGI researchers. And then the system has some knowledge about how a few works, and then they can draw that conclusion eventually. And I mean, that can work. I mean, you can't argue against that. But when you actually try to do that, you run into many other similar problems. So the basic thing is to do this kind of inference using PLN is a simple matter with conditional probabilities and Bayes rule and so forth. And to do this kind of inference using NARS becomes quite complicated because you don't take into account the term probability. You don't take into account how many of these there are. Now, for Pei, that's really a matter of principle. He just thinks term probabilities are wrong, and the mind doesn't use them. And to my mind, I kind of think Bayes' rule and elementary probability theory are good, and we should use them. Now, of course, the brain doesn't use those exactly, right? I mean, we're not that great at probability reasoning. On the other hand, I think we sort of roughly approximate it. So I have a paper on this I'm giving at the workshop on there's a workshop at the AGI-13 conference called Probability or Not, which was organized by Pei and one of my OpenCog collaborators, Matt Eclay. Now, unfortunately, there's no one who submitted a paper arguing not to use probability theory. I mean, Pei has already written papers on that. He didn't have anything new to say just by writing a paper about it. But, I mean, there are different ways to use it, you know. So what I showed in that paper is that there are some existing proofs showing that basically if you do reasoning in a consistent and coherent way, you must be doing probability theory. So there's kind of axiomatic derivations of probability theory going back to Cox in the 1940s. So what I showed in this paper is if you reason in an almost coherent and consistent way, then you must almost be following probability theory, just by propagating some epsilons and deltas through someone else's proof. So, I mean, of course, you can never really resolve this with mathematics, but that's sort of the way I think about it. Like, you're introducing some incoherence by not obeying probability. To me, that's like not obeying 1 + 1 = 2 or something. And of course, we don't do that exactly right in our brains, where we kind of approximate it. But, I mean, when we really dig into this argument, he could write out a complex set of knowledge and a logic for dealing with few and many that makes his system come out with a decent answer there. But I guess part of the motivation for me in developing an uncertain logic was to have something where the inferences that were simple and natural to a human are simple and natural in that logic. And then, of course, you get into debates among what's simple and natural. Because to me, this is a simple and natural inference. To Pei, it's a very complex probabilistic inference that involves a logic of fewness and manyness and so forth. So anyway, that's the direction the argument would go in if he was here. He would explain how to do this by introducing a bunch of extra knowledge about how many AGI researchers there are. But so the crux of it comes down to, if you're going to use probability theory, you need to have term probabilities as well as link probabilities. Pei thinks term probabilities are cognitively unnatural, so he made up a logic that tries to do inference without term probabilities. However, if you look at the truth value formulas for his induction and abduction rules, they're quite weird, actually. Like, I think his truth, if I'm remembering right, the truth value for this wouldn't depend on the strength for this wouldn't depend on the strength for this at all, for example, but only on the strength for that. So I think those truth value formulas are weird, and when we tried to implement them in a bunch of cases, we couldn't. I felt less strongly about this around 1999-2000 when we were first playing with it. We tried a bunch to get sensible conclusions out of it from a decent-sized knowledge base and did not succeed. But that's not to say that Pei could never succeed either. I mean, I think like all the parts of the system have to work together. And in the case of OpenCog, in this respect, it's easy because all the parts operate coherently with probability theory, which is well understood. And so, I mean, you can have a vision system output the probability that there's an object here. You can have a program learning system have the probability that the program will carry out a certain action given a certain input, and you can propagate probabilities through logic. Now, in Pei's system, somehow he'd have to make perception language and all these other subsystems that work coherently with his unusual logic, which I can't say is impossible, right? But it's hard anyway. But I admire his guts anyway. I mean, I usually prefer to be a nonconformist just by personality. So I would rather be advocating a weird logic no one else likes than probability theory, which is boring and everybody likes it. But unfortunately, I actually think probability theory is right. So then Moses, this is actually something I've been working on a lot personally in the last year, and I'll talk about that in depth later, but this is an automated program learning algorithm, and basically solves the problem of learning a program given a specification. Of course, if you solve that problem thoroughly, you wouldn't have to do any more programming or any AGI programming. You just specify what you need your AGI to do, and then Moses would write the AGI for you. And there's nowhere near that level of sophistication, but for simple programs, Moses can learn a program given a specification. And we've actually been using that a lot recently just as a data analysis algorithm, like learn classification rules or learn predictive rules to predict a time series given its history and so forth. And that, we've done a lot of work on that, and that work is ongoing. And that's something where we've used that a lot just as a machine learning algorithm, ignoring the rest of OpenCog. So you can run it from the command line separately than OpenCog, or you can use it together with the rest of OpenCog. And that's, I think, at this point, is a very, for certain kinds of machine learning, it's probably the most powerful thing there is. And we're improving it actively as we speak now too. I mean, some of my colleagues are. So that's, I mean, how central automated program learning is to AI, again, depends on your opinion. Like in theory, if you solve automated program learning, you're done. But in practice, the space of programs is quite large. So I think what we're looking at now is learning programs with like a couple, if you represent a program as a tree, where the inputs are the leaves of the tree, and then there's control operations in the nodes of the tree, you're looking at learning programs with a few dozen nodes in the tree, so it's pretty small. Now, if you could get up to programs with a few hundred nodes in the tree, say just like maybe 1 to 1.5 order of magnitude increase in the size of programs you could learn, then you have something pretty interesting, because I think the typical like cognitive control program, let's say a program doing the essence of PLN inference, or very simple program learning or attention allocation, you could probably pack that into like a program tree with 500 nodes in it if you use your functional language. So then if you can make a program learning algorithm learn programs with like 500 nodes in the corresponding program tree, then you can make a system that learned, in principle, it learned its own cognitive control modules and made itself smarter and smarter, which would be quite interesting. So on the one hand, we're only 1 to 2 orders of magnitude away from there. On the other hand, when you're dealing with like things with factorial explosion and complexity, that's a long way away, right? So how far you can go with program learning as a paradigm, I'm not sure. I mean, and maybe you're only stuck with learning fairly small procedures and using inference to chain them together into more complex things. Let me see. Oh yeah, there's more AI parts I haven't talked about, but let me just proceed through this presentation just because it's here. Right? After I go through this high-level overview, I'll go back and look at specific parts of the AI in more detail. So OpenCog, as you've seen, is a fairly broad thing, and you can use some parts of it as tools in building narrow AI applications. You could build many different AI architectures on top of it if you wanted to. And I think to really move toward AGI, the best thing to do is to use it to control an embodied agent in some world. And it's better if the world like vaguely resembles the everyday human world, because in that context, we have a good idea of what tasks are easy, what tasks are hard, what sequence things should be done, and we can interact with the agent in that context. I mean, I don't think that's the only way to do things. Certainly you could make an AGI that did nothing but prove math theorems, for example. And as a mathematician, that would appeal to me somewhat. It's certainly easier than messing with robots in game worlds and so forth. On the other hand, that's a very alien kind of mind, you know? And it's hard to understand what's going on inside it and how much progress it's making. So what we have been doing is working on a proto-game AI. Which is why we pulled in Lake, who's an experienced game developer. And we're not presently trying to make something that is going to be a big game and a lot of people will play, but we're making a technology that we hope, as well as advancing AGI, we hope that technology can eventually be integrated into a fun game that people will want to play. And possibly the prototype work that we're doing now could be extended and enlarged considerably into a game that would be fun for people to play. Lake has had a bunch of ideas about that, but right now we've just been looking at a game world as an environment for prototyping the OpenCog ability to control agents. Like most things, it's turned out to be a lot more work than we thought, so just getting a decent game world and connecting it to the OpenCog system has been a lot of work. And we finally have gotten our Uni 3D game world connected to the OpenCog embodiment component, 2 days ago or something?
Fully connected, yeah.
Yeah.
And on and off for months.
Yeah. Is it working now?
And it seems to be working.
Cool. So yeah, this has been, we have 5 people working on OpenCog in Hong Kong. So, and most of these are with an AI orientation. So Lake has been working on the game side, and then one of our AI developers, Kesh Shujing, had experience doing game development in the game company, and she did a bunch of work on the part of OpenCog called Embodied, which kind of sends messages to and from the game world and deals with perceptions and actions in the game world. So right now, we've just barely gotten the connection to work, and so that the agent can do simple behaviors in the game world that's triggered by OpenCog. And then our job in the next couple years, which we have funding for from the Hong Kong government, our job in the next couple of years is to get more and more of the OpenCog AI modules actually doing useful stuff in the game world. Now we had some earlier, simpler versions of the game world working and connected to OpenCog, and so we did some prototype examples of OpenCog controlling an agent in the game world to do some specific things, which was interesting and taught us something. But both the game world and the interface between OpenCog and the game world were too simplistic, whereas the way we have it now still has a few hacks in it, which will be removed in the next few months by Lake. But by and large, it's a robust framework that we can use for more and more intelligent embodied behaviors. And I think the advantage of a game world is, everything that happens in the human world happens in some simplified form in a video game world. You have perception, you have action, you have language processing, you have social interaction, you have planning and learning, some space and time.
People shooting each other?
Well, we don't have that in our game world right now, but if you want to hack it into the Unity world, you're quite welcome to. It wouldn't be hard.
AGIs are going to be trained to shoot people.
Well, not every game is like that. So, yeah. Yeah, Nate, but why don't you describe your thinking about the game world for OpenCog?
Sure. Well, we set up for a simple test for it. While I move to the front, actually.
Oh yeah, stand next to me. You can be picked up by my microphone.
Yeah, right. So for the game demo that we had in mind, we thought that we would make it just a bit simpler by making a Lost Vikings, or trying to think of a more modern example, Trine, if you played it. These games where you play as 3 characters normally, each one with complementary skills and abilities, and you try to accomplish a task, whatever the task is, like usually some type of puzzle, not as often shooting enemies or trying to defeat foes. Our premise was that, unlike most of these games, where you control all 3 characters one at a time, and you can switch at any time, you can only control 1 character at a time, and the other 2 are controlled by OpenCog. And so the premise is that OpenCog learns how to use the unique abilities of each of the characters to aid you to solve puzzles and complete levels. So that was the basic idea that we had. Right now it's not all the way to the full game concept, but we do have the 3 characters. They each have unique abilities, and you guys can build puzzles and design AI to try and solve it. So
Yeah, the 3 characters are a ghost, a robot, and a little girl. Huh? I think she looks like Lake, you think?
I think so too. You have to squint your eyes more. Where's the tickle monster?
we do have the tickle monster. You can see a small image. But yeah, that's the only enemy that we have right now. So we'll talk about that more later.
Yeah, but I mean, ultimately, of course, if we were to get this working better and package it up as game AI middleware, then it could be used within shoot-'em-up games or basically whatever. Chester the Molester online. I mean, I think though that the kind of capability that OpenCog offers for a game, it's not ideal for like Doom or Quake or Halo or something, because I mean you can make AIs for those things using different methods if you really want a better AI for that particular kind of game. I think the more kind of wide open and sandbox game like the game is, the more opportunity there is for like a young learning AI to participate in the game. So if I'm not nearly as much into games as Lake is, but I watch my sons grow up and play a lot of games, so I saw them at second hand. Look at Metal Gear Solid 4. My son Zeb played a lot. That game is like a movie. Like you have long cutscenes, and then the actions you have to do to get through it. It's pretty scripted. Like they know what you're gonna do in advance, right? So I mean, for a game like that, an AI that can learn and do flexible, weird, random things is just gonna mess with the gameplay. Like the next cutscene would make no sense based on what the AI did. So you need games which are a bit more wide open in terms of what could happen. I mean, the Grand Theft Auto would work. I mean, you could have an AGI crack whore going around or something. I mean, a game, just because in that game you go around and do stuff, and it's fairly wide open. If one of the AGI characters did something weird and unexpected, then it's not going to break the whole idea of the game, because it's not this carefully scripted series of things. So I think there's one idea Lake had is that there are people who like big, complex games with many players and long quests and complex worlds, but get sick of the stupid, annoying behavior of the other human players. So if you had AGI players, then you could have the experience of playing a big, complex multiplayer game, but then the other players are AGIs rather than people, which shows a variety of advantages. I mean, you can start and stop with it whenever you want, and you have different social characteristics.
You wouldn't need real friends either.
Well, yeah, that's another point. Yeah. People who play games that much don't have friends anyway. So it's all right. Yeah, so we have the three prototype characters, and the idea is that the character is controlled by this whole mess of OpenCog with the atom space and perception action and all these different cognitive modules there. So we've done some prototype experiment with earlier versions of the game world. This is something we presented at the BICA 11 conference. This is an earlier version of the game world with a bunch of blocks, just getting the AI to go around and do very basic things with blocks. We, for example, learning to build a staircase, by example, like it watched someone to build it. It watched the girl build stairs, as controlled by a human, and then the robot build stairs on its own because it saw it being done. So it knew it's a reasonable series of actions to carry out. So this just shows kind of what happens in the world of the robot. The robot, was supposed to.
You lost it.
Huh.
Do you have this slideshow set
I could show that later. It's not that exciting anyway. But the robot just builds stairs until it gets up to the top of that platform. Huh?
Is it doing their goal?
Yeah, that's right. Because it wants to get that gold thing at the top. It knows it will get goodies if it gets the little gold box up at the top. So it's going to keep building stairs until it gets up to get that gold thing up at the top.
Are these characters, do they get rewards for good behaviour and then repeat that behaviour sort of thing?
In principle, what they get now is they have a set of goals. So, for example, it can be an energy goal. Like it wants to keep its energy high enough, and a safety goal, meaning it doesn't want to have anyone killed or something. So, and it knows if it eats that box, it will get more energy. So then it's just a reinforcement learning sort of thing. Now, you could also give it a little button like good robot, bad robot, and then you give it a goal of get reward from the human. And we haven't actually been doing that, but it will be a very simple modification within the framework. So the idea of this particular world, which Lake and others have built, is inspired by the long history of blocks worlds in AI. I mean, if you go back to Schödler and like old AI systems from the 70s, and I mean, but here we have more blocks, right? So, I mean, you're always open to people mocking you and saying, well, AI can only deal with blocks. How can it ever deal with the real world? But, I mean, of course, it's a prototyping environment, and we're intentionally making a simplified environment. And if you were starting out to architect a system specifically for dealing with blocks, then there's a valid argument that, well, why is that actually so interesting? But since we started with a system architected for more general intelligence and are then just using this world to kind of test and refine its capabilities, I don't think it's a problem that the world is simplified. I mean, I think that, to me, that's a feature rather than a bug. We wanted something simplified so that it's easier to do experiments. And so what you see is the tree is made of little leaf blocks and trunk blocks. Like this wall is made of bricks. This hedge is made of little plant-type blocks. And the point of that is that because all these things are made of blocks rather than being like structures built in Maya or 3D Max or some graphics program, because these things are made of blocks, the AI system can potentially understand their composition. Like it can understand, okay, that part's the trunk, that part's the top. Now, these two parts are similar, those two parts are similar. Oh, the top of the tree is a lot like this bush, right? So I mean, if you ask it to make the tree taller, it might be able to figure out to grab hunks off the bush and put them on top of the tree, for example. So, because it understands the inner makings of the things in the world. And without that, really, the virtual world is completely opaque to the AI, which isn't good. So I mean, if you're going to not use blocks or something like that, I mean, in Second Life they call them prims for primitives. If you're not going to use something like that, then you really need to give the system the ability to understand the 3D shapes and curves and contours that the things in the game world are made of, which is also possible. I mean, we've thought a bunch about that. I mean, there's existing software for taking a 3D contour and making a skeleton out of it, and you can reason on that. So that is another meaningful direction to go in. But the blocks world seemed like a tractable place to start. Anyway, and indeed, just getting a good blocks world up and running and communicating effectively with OpenCog has been complex. But I mean, of course, that's why building a game takes a team of a number of professional programmers a number of years. I mean, there's a lot to do. And we've been trying to build a sort of game-worthy world with basically one game programmer. So it's, yeah, here, let's see, is this going to work? Maybe. Oh. this was basically just showing the system pathfinding. So this is an earlier version of the game world rather than the one we're working with now, but which was built by some folks before Lake came on the project. But actually, someone said they're from Wellington, right? This was built largely by a guy named Joel Pitt, who is now he's from Wellington. He's in Wellington now. You know Joel, do you?
Oh, yeah.
Yeah, what did he do? I think he goes to like bar camp and various tech events there all the time, so it's not impossible to run into him.
Probably run into him at some stage.
Yeah. Yeah, what was he at the Kiwi version of Burning Man? What's that called? I can't remember. Like 200 Kiwis out in the forest somewhere. Yeah. That's right. He's always at those things. He's a electronica DJ as well as an AI programmer. But he's not been active on OpenCog much for the last year. But anyway, he built a lot of this game world.
So that's the avatar there. Is these little robot things controlled by?
These are that's happiness. That's excitement. That's fear. That's anger. So those are the levels of different emotions inside the system as it goes about and does things. This was, while the world was built largely by Joel, these demos and the emotional motivation system underlying it was programmed by a guy named Shai Zhenhua, who was doing his PhD at Xiamen University in China. And he wrote his PhD on basically emotion and motivation in an AI system. And
Why is he always sad?
the robot, I don't know if
His happiness is way low.
it's a crappy little robot, right? I mean, it's gray and gloomy. All he has to do all day is run around and get those batteries. You'd be sad too, right?
So OpenCog is. Did you just write a pathfinding algorithm and tell OpenCog to go use it, or does OpenCog actually work out how to do its own pathfinding or something? Or what?
A mixture of the two. So there's like pathfinding operations in there, but then it learns when to use the pathfinding operations. So. Actually, we've done both. So we have an A* implementation, and then we also have used PLN inference just to do planning, which is quite slow. So now. The thing is, what we want to do now is use the pathfinding algorithm when you can because it's fast. But let's say you're trying to find a path to get that up there. If you're just using A* or standard pathfinding algorithm, if it gets here and it can't climb up here, it might run around in a circle and then give up. So then you need to invoke some other process to figure out to build steps to go up there and get the thing. But then when you're in a situation where a basic planning algorithm can get you where you want to go, you would just invoke that and use it to get where you want to go, basically. So, yeah, so another thing we've been doing in a different earlier prototype version of the game world is an algorithm called Fishgram, which stands for Frequent and Interesting Sub-Hypergraph Mining. I'm quite proud of my ability to come up with strange acronyms. Learned from working on U.S. government contracts. Like, if you're applying for a U.S. government research grant, of course the most important thing is whether they know you and giving you money before. But apart from that, having a good acronym is probably the second most important thing. I mean, they have enough attention span to read the acronym, maybe not to read the proposal. So. I think we also had sushigrams, surprising sub-hypergraph mining, but that never saw the light of day. Right? So basically, the atom space, the nodes and links making up OpenCog's memory, it's kind of a graph because it has nodes and links, but it has a couple peculiarities too. I mean, it can have a link. It can have a link spanning more than two nodes, and that makes it a hypergraph rather than a graph. Now, as it happens, it can also have a link that points to a link, which makes it not even a hypergraph. But I mean, you can always say, well, there's an invisible virtual node here, so I'll call it a hypergraph. But it's a generalized hypergraph because it has links that can span many nodes and links that can point to links. So what is a sub-hypergraph? Well, it's part of a hypergraph, right? So frequent sub-hypergraph mining means finding patterns that occur over and over again, basically. So like, let's say you had a database of knowledge about a lot of people, and it turned out that, say, I don't know, there's a lot of Jewish AI researchers, which is true. So you could learn that as a frequent hypergraph, a knowledge about people. There are many people that inherit from Jewish and inherit from AI researcher and human. And that sub-hypergraph occurs frequently in the graph. And applying that to the game world, so we applied that to some simple game world situations just with a bunch of different objects sitting around. Yeah, like we've lost that cool leg helicopter in this current world. Huh?
Yeah.
Yeah, that's kind of funky looking.
It didn't really serve any other purpose than to confuse OpenCog.
No, but it looks cool. Yeah. Yeah, who designed that?
I don't know. Probably Joel.
No, Joel didn't build it graphically though.
Oh.
Oh, Troy? Yeah. Oh, all right. Yeah. Yeah, so here we see a bit of the detailed node and link syntax, which we tend to write out in kind of Python or Haskell style indent syntax. So we have, this is a pattern that the sub-hypergraph miner recognized in a bunch of different, in a kind of video of game world like the previous slide with a bunch of objects sitting around and the agent going around doing things. So this basically says that batteries are edible. So because, so this is a variable. It's an atom with the atom handle, the address 100041. So and link, so that's a logical conjunction of inheritance link. The thing is a battery. It's a concept node called battery, and a predicate evaluation link between the is edible predicate node and that entity, which was a specific battery. So this had many matches. So there were many. In other words, you could match this variable to many specific nodes in the atom space. So it meant that in many cases it found something that it could eat and was a battery. And now what do you need for this to be possible? You need some wiring that basically says if it ate it, then it's edible. So it could go around trying to eat things. Well, I tried to eat this, didn't work. I mean, in this case, for us as humans, to tell if something is edible, it's harder. We put it in our mouth, we could swallow it, see if we throw up or something, right? For the AI in this world, I mean, if it puts something that it can't eat by its mouth, it doesn't get any energy, right? So it's a little more straightforward. It doesn't work. But that's a simple pattern that occurred frequently. Now, this pattern says that it's holding a battery. So again, over many instances of time, you have data coming in from the perception world, perception data coming in from the world about the system's body and about the things in the world. So it knows what it's holding. So over time, it's holding something which is a battery. And this is him, and that is the battery. Now here's a more interesting one. When I eat a battery, my energy demand is fulfilled to some degree. So you have, when the action of eating the battery is done, then the energy demand goal is increased. So I mean, it's just basic recognition of patterns in what the agent is doing in the environment. And none of these are very large. So what you can see here is there's some artistry that went into giving it like the vocabulary of nodes and links to use, right? So it has a certain set of demands, which are its basic drives. One of them is to get more energy. So there's a node created for that, the predicate node. Then increase, okay, we made a predicate for increase. So it doesn't have to learn what increase means. It doesn't have to learn like, okay, my energy now is greater than my energy at some previous point by more than this threshold. We built in the increased predicate. And of course it knows when it did something. So execution link of the grounded schema node eat means that procedure to eat was executed and that action was completed. So of course there's mechanics hiding there. A grounded schema node, so a schema node is a node wrapping up a procedure. A grounded schema node is a procedure the system can do itself. So, for example, the system, it can't fly. Say, well, the ghosts can fly actually. So in the games, that's not a good idea. It can't spit. Well, there's no spit animation. So if you have the action to spit, that would be an ungrounded schema. It's just a schema node. And it may know what that is. It may be able to reason about it, but it doesn't have that built in as an action it can do. Whereas to eat, in this case, that's grounded by something in the game world, just like walk is and some other basic things. So by crafting the right set of basic concepts and predicates, you make it so that the patterns that are useful and meaningful are relatively small and can therefore be mined by relatively simple algorithms. So, of course, you can cheat that way to make the system look like it's smart, because if you just know what patterns you want to recognize and you code a vocabulary of nodes and links that makes those patterns compact, then a fairly dumb search algorithm could find the patterns that you want. On the other hand, that kind of cheating is partly what evolution did. Like we're good at recognizing stuff that evolution recognized we would commonly want to recognize, and that's kind of how the human mind works. Like if you test people on abstract puzzles, they may do badly. Then when you cast the same puzzle in the form about like people stealing their money or their girlfriend or something, then they'll be very fast at solving that same puzzle when it's cast in concrete terms. So we're better at solving problems in the concrete context that we have evolved for, and that's easy to see. Like in some classic psychology experiments, I mean, you ask people to estimate various things about probabilities, and they're terrible. Then you ask them, like, would you take this bet in a certain context? And they're very good at reasoning about odds and betting, even if they don't have much education. Because that kind of triggers some wiring we have to want to win and judge the odds of getting a reward or not, right? So, I mean, there's a fine line there between whether you just customizing it in an intelligent way so that the things in its environment are compactly represented, and whether you're like hacking it so badly that it won't generalize beyond the exact little world that you've created. So, yeah, I won't say too much about language processing because Ray Ting is going to talk about that probably tomorrow. But we have some language processing tools associated with OpenCog, and on the one hand, some of these work pretty well. On the other hand, they're not built in that AGI-ish of a way. So the language comprehension toolkit is somewhat mature. I mean, we can take English sentences and turn them into OpenCog nodes and links in a way that represents the semantic content of the nodes and links. But I mean, we do that using the bunch of traditional computational linguistics tools. So we use the link parser, which is an English dependency parser. Then a bunch of rules written on top of that abstract the output of the link parser into something more semantic oriented. And Ray Ting is in the middle of working on another set of rules that map the output into something even more abstract and easier for reasoning to work on. And that whole system, it's state of the art as computational linguistics. When we compare it to other things that are better known parsers, they don't work any better. In some ways ours is better. But what you'd really like, of course, is a system to be able to learn language just from experience, just learn language as another skill. And in essence, we built these tools for various commercial contracts where it was useful to have language processing that actually worked. Whereas trying to have the system learn language just from experience is a very long, hard research project. Now, what I'm hoping we can do is use this existing linguistic knowledge to bootstrap the system. So have it start with this existing knowledge as step one, and then revise the linguistic knowledge from there. Now, the current implementation of the language processing system doesn't really support that, because what we would need is basically all the union-created language processing rules to be in the atom space as nodes and links. But in the current implementation, the specific language processing rules are in other files in a specialized format for parsing and semantic interpretation. So this sort of goes back to the thing I raised much earlier today of to what extent can narrow AI systems be kind of combined together to be useful for AGI. In this case, I think in principle it can work to use these narrow AI language parsers and semantic interpretation systems and use them as the initial knowledge base for ongoing language learning. So you can start way above zero and have the learning algorithms improve the language understanding. But in practice, the way the parsers and semantic interpretation systems are implemented isn't really friendly for that. So we at some point, I want to re-implement the language processing tools in a more AGI-friendly way, and that's being done kind of as a background project. A guy named Linus Vepstas, who's an OpenCog volunteer for a long time, he got halfway through implementing a new version of the link parser that would be done in a very AGI-friendly format with all the rules represented as OpenCog nodes and links. But then he got distracted by his paying job and hasn't had time to go back to it for a while. But Linus and I are in the middle of writing a proposal for how to do all that right and really do language learning properly in OpenCog. And we will attempt to get Google or Yahoo or Microsoft or some big company that does language processing to collaborate with us on it, because I think these companies would certainly benefit from that, and they have the computers and the data that would help feed something like that. I think after a certain point, you're going to need embodiment. Like there's a certain amount of language understanding you're only going to get from having a body and interacting in the world. But it would be interesting to see how far you could go just by crunching a huge amount of text within OpenCog as well. So anyway, Ray Ting will talk about and show a bunch of examples probably tomorrow of the language comprehension pipeline. She also built a prototype language generation system a couple of years ago, which wasn't that flexible, but showcased the idea of taking nodes and links and turning them into English. And we had a design for a better way to do that, which either she or someone else will do in the next year. And then the other aspect is dialogue control, like how to decide what to say at what point in time. And for that, we don't have hardly any of that in there now. We had a very simple dialogue system in there a few years ago, which with specialized for certain kind of conversations in the virtual world. But what I want to do is make dialogue control just another aspect of action selection. In other words, you could choose a speech act just as well as you choose any other act. So let's say I want to have that door opened. I mean, one thing I could do is walk over there and open the door, and then there's no speaking, right? And the other thing I could do is use words and say, hey, could someone open that door? And then that might achieve the same goal, right? So I think choosing what to say and choosing what to do can be done as part of the same process of basically largely goal-driven action selection. And that is different than what is done in most dialogue systems. But if you look in most of the dialogue control architectures in the field of automated dialogue systems, these tend to be oriented toward making dialogue systems that serve some quite specialized function. Like you have a kiosk where someone can make ticket reservations, and it's talking to them about that, or it's a QA agent trying to find out why your computer's broken. And within that context, you can keep a kind of task-specific state model of what the user knows and wants, and you're just dealing with a bunch of dialogue control rules. But of course, a more open-ended dialogue, like a young child has, or an advanced AGI has to have, the more open-ended dialogue can't be done with a set of scripted rules for what to say when. And I think it has to be done kind of a piece with learning to act, basically. So comprehension is fairly mature, and by the end of this year should be much more mature, because Ray Ting is doing a bunch of work on that, along with Kevan, the guy in Isfahan in Iran. And generation, we had a prototype system which taught us that we want to build a different kind of system, which we've designed and not built. And then dialogue control, haven't really done much on. However, it's going to be the same control framework that we use for action control. So there's not a lot of specialized work to be done there. And Ray Ting is going to go over these particulars of the language system tomorrow, so I won't do it now. Now,
Excuse me,
yep.
I have a question about these schemas and the actions
Sure.
that you were talking about.
Yep.
Am I getting right that this agent have some bunch of schemas and some bunch of actions that he can experimentally experimentally play with to find something useful?
Right now there's like a bunch of atomic procedures that the system can do. Like in the game world, like take a step forward, turn right, move your head to the right, reach out and try to grab something. So they're fairly high level compared to like the servo motor commands of a robot.
And it experiments with it to find some new ways of action, or how.
Well, it's trying to sequence together basic actions to achieve its goals. And I mean, we did some engineering of what the actions are. Like if it sees some object, an action can be go to that object, and that's fairly high level. I mean, but we chose that instead of going to a certain coordinate location because it's easier to learn things. We'd go to that object, because then if the object is moving, it can be a lower level function to modulate where it goes to follow the object. So that's, it's basically, it's not adapting the particulars of action execution. Like it's not adapting the way it walks or the way that it reaches down to pick something up. It is adapting and learning the way it sequences actions together in a row to achieve some goal it wants, like being safe or getting energy or finding a hidden object. And that's that's how the system works at this moment as a practical software system. I mean, ultimately, in the overall OpenCog AGI design, we would like the system to be able to learn to act as well. I mean, we need to do motor learning, just like perceptual learning and so forth. And then for our initial foray into robotics, actually the robots we're working with also have basically canned animations, like step forward, pick this up, turn your head to the right. So you can kind of treat it a lot like the game world, really. It's just slower, and the feedback you get is more lossy. But ultimately, you need the system to be doing lower level stuff and issuing action commands in a more flexible way. If you want to do something like eye-hand coordination or something, or pick say this bottle had liquid in it and was open. If I want to pick that up, since I'm not that retarded, I don't just just do the same motion. I think like, okay, that has juice in it. No, maybe I should pick it up and keep it oriented vertically the whole time, right? And I mean, when you have young children, you can see them getting to that point, like between the age of 6 months and 1.5 or something. They figure out how to modulate picking things up in a way that makes sense based on what they're picking up. And we've thought a bunch about that. I'll talk about that later, but we're not doing that now. I mean, that's where you need a sort of action hierarchy correlate with the perception hierarchy and a bunch of deep learning type stuff. So what I wanted to talk about now is the motivation stuff. How does the system choose what it wants based on its goals? And for that, we borrowed a theory of motivated action from a friend of mine named Joshua Bach, who spoke at the previous AGI Summer Schools, the German AGI researcher. And Joshua Bach borrowed much of his thinking on this from a guy named Dietrich Dorner, who is a German psychologist who wrote very little on this in English, however, and my German is bad, so I mostly read what Joshua wrote. No. Joshua's book, The Principles of Synthetic Intelligence, is quite good. I mean, I don't agree with everything in it, but it's a good book, and it reviews Joshua's perspective on AGI, and then discusses a bit of his concrete work with his micro-psi system. So Joshua's micro-psi AGI system, or proto-AGI system, whatever, is, I think, a pretty good approach. I mean, we borrowed only part of it for our system here. We borrowed the basic logic of motivations and goals and action selection. He also has a specific knowledge representation based on a neuron-like unit called a quad. And we did not try to borrow that neuron-like knowledge representation in OpenCog because we use the atom space, which is a quite different sort of thing. So we borrowed part, but not all of his system. And yeah, you can see throughout OpenCog there are various things that have been borrowed from other people's AGI work, often, however, distorted or utilized in a way that their creator doesn't like. So, I mean, from working with Pei a while, I got interested in term logic and imprecise probabilities and so forth. So a lot of PLN is sort of NARS-like, but ultimately it's not, because we use probability theory, which Pei doesn't like. And then we use term logic, which is sort of like NARS. But then, in the case of motivation, I borrowed this psi model from Joshua Bach because I thought it made a lot of sense. But his knowledge representation we didn't take. And a little later I'll talk about vision processing. We're using this deep learning system developed by Itamar Arel, which is nice, but Itamar is really looking at that as the foundation of the AGI system, whereas we're using it as basically a sensation module. But yeah, I mean, I think if I'm right, the different parts of the human mind have different sorts of architectures that need to all interact with each other, then it would make sense that some researchers may have adequately solved the problem of one component of the integrated mind system. So the action selection thing is relatively simple. I mean, you have basic urges or drives, and these in both OpenCog and Josha's framework are pre-programmed. So urge could be get energy, get a reward, have safety and stability, or more interestingly, an urge could be experience novelty. So, yeah, it was interesting. Troy Wang, Deheng Wang, who was working on this for a while, he looked at the motivational system. He was like, no, you left out the most important one. You left out the urge for social acceptance. So I thought that was a very Chinese addition to the system. Like, being built by Americans and Germans, we didn't think of putting social acceptance as a basic urge. But Troy thought that had to be there in the base of it. So. Well, anyway, so in that way, the motivational system crafted by him would be a little different than one crafted by me, because I didn't put that at the base level. No? You could say that will emerge from some other desires. That should emerge from the desire to get rewards. If people only pat you on the head if you do what they want. So there's some artistry in what you make the basic goals. I mean, of course, in the reinforcement learning paradigm of AI, you would just make one goal, get a reward, right? And then everything else comes out of that one goal. And you can do that. On the other hand, if you have a young mind that's not very smart, it may take it a while to learn how to get a reward in this or that setting. And if you give it specific goals, specific properties of its experience that it's motivated to achieve, you can make the learning faster and more intuitive. I mean, ultimately, the idea of get a reward is kind of an abstraction of a bunch of other things. So, I mean, even in the human brain, there's a whole bunch of different chemicals in there that all kind of act as rewards and motivate us. Yep.
Just mentioned the novelty preference as a drive. Do you know how to do that? Do you know how to tell if something is novel or not?
Kind of. I mean, we use information theory.
Oh, okay.
Surprisingness based on mutual information. I mean, there's a notion of absolute novelty, like was it ever seen before in the world? But that's not really what we're after. We're after is it novel to the system in its own experience. I mean, just like a little kid can be excited when they discover something for the first time, right? Well, I mean, I can be excited if I discover something, new piece of mathematics, because it's new to me. Then I'm disappointed next day when I find someone published it in 1950. But there's still that novelty drive that makes you happy to have discovered something you hadn't seen before. And without that, the system will be very boring, actually. I mean, as we found empirically from playing with earlier versions of the game world, like it will try to get a reward, and then it will sit there and not do anything if it's satisfied, which is a reasonably common human behavior pattern too. Right? So, yeah, in the psi framework, there's usually one current leading motive. Where there's one goal that the system's focusing on at any one point in time, and the other goals are kind of there in the background. And then there's a number of parameters called modulators that modulate the way it perceives this goal. So one modulator would be like, how much of a hurry is the system and how much pressure is it feeling? And that controls a bunch of other parameters in the learning system. So this basic framework of I have a bunch of goals, I choose one mode of them primarily pursuing now, then I choose an action from all the possible ones based on that motive, then I send that action off to get executed. I mean, it's a pretty basic and simple framework. And what he goes into in his book is the different parameters that modulate action selection and planning and so forth. I mean, I think the issue I have with the current version of Josha's micropsi framework is that there are no powerful learning algorithms in it. I mean, it's a sensible framework, but the learning algorithms there are all things that would never scale up to large problems. And I mean, Josha knows this. He just wants to get everything working together in a sensible way and then plug some scalable learning algorithms into it, which is not a stupid way to proceed. On the other hand, if your knowledge representation and framework turn out not to be amenable to building scalable learning algorithms, then you're going to have to go way back to the beginning to deal with that. So actually he has been rewriting the micropsi framework for much of the last year. The previous version was written in, I can't remember what, some horrible Microsoft only language. And now he's rewriting it in Python. Right? And
Java.
was it Java?
I think so.
Really? There was something weird about it, but I can't remember what. Yeah. Maybe that was 2 versions ago. Yeah. Anyway, he was rewriting it for a variety of reasons, and he gave a talk on micropsi 2 at the last AGI conference. Yeah, so here are some basic dynamics of the psi architecture. So we have the resolution level. That's basically how much detail is the system trying to understand the world at. And that boils down to parameters in a bunch of different learning algorithms. How much effort do they expend on learning something, and do they just try to come to a hasty conclusion? And that depends on how much of a hurry is the system in. Like if it's about to run out of energy, the resolution level should become quite low. It doesn't care about understanding things in detail. It just wants to get to food, get to the battery, right? The arousal level is kind of how much energy does it have, how fast is it moving, how many things is it doing, how goal-directed is it, like how much of its energy is it spending trying to achieve goals versus just existing and letting the activity propagate through its mind. Selection threshold means what is a threshold for changing from one motive to another. Like how single-minded are you? So yeah, the securing threshold, let's see. I'm almost forgetting what that was. Let's see. I actually forget what he meant by that. I don't know. Is that still in there? What the hell is the securing threshold?
I think securing threshold was something like the threshold at which it is considered to be home, like secured.
Okay, so how easily is it made to feel safe, basically?
I think so.
Yeah. Okay, so then in terms of these basic parameters, Jemois defined these emotions as corresponding to them. So if you're angry, you have high activation, you're active, low resolution, you don't really care about the details. It's very hard for you to feel safe. It's very easy for you to change from one thing to another, and you're not very happy. So this is a simplified case, but it's a special case of Joe Shabbat's overall theory of emotions, which is that the emotions kind of emerge from the system based on various properties of the motivational system. And Josha has a chapter in his book where he plots some higher dimensional space of all the different parameters of the motivational system and looks at the different emotions as different regions in that space. And this this simplified version is an example of that from Jamar's PhD thesis. And this is different than one simple thing. Like you could make like a happy node, a sad node, an afraid node, and so forth in the system. And just have those motivate the system's behavior. But in this approach, the human-like emotions are understood as sort of descriptions of certain combinations of underlying properties of the motivational system. And of course, this psi model is a big oversimplification of the human motivational system, but it is, I think, a vaguely human-like motivational system anyway. And then there's an interface which lets you graph the movement of these various emotions over time. And like this doesn't work with the current game world, does it?
With the emotional stuff, not that by itself.
I guess it shouldn't be hard to reactivate.
Probably not.
So yeah, with the previous version of the game world, you could go through and basically make graphs over time of the different emotions and the different underlying motivational system parameters and see how they fluctuated. So sometime in the next couple months, this will be hooked back up to the new game world. Actually, if someone feels like getting into OpenCog programming, it's not a terribly hard project, I would imagine. Right? Yeah, this is a previous version of the game world. This basically shows the little OpenCog controlled robot. It has two basic goals here, security and energy. It feels secure in its house, and it gets energy when it eats a battery. So basically what it does, it sits in its house until it starts to run out of energy. Then it goes out and eats a battery. Then it's full. Then it goes sits until it runs out of energy again. It's a lot like a rabbit, actually. I mean, rabbits will just sit, they're very fearful. They'll sit in their hole until they get hungry, then or want to have sex or something. Then they'll go out, they'll do what they want, and they'll go back and hide in the hole, right? So it means rabbits are not very curious animals. I mean, I used to own a bunch of rabbits. I had one who was very curious, but that's unusual. Most rabbits are not curious because they're too fearful. And if you're curious, you're going to put yourself in some danger, right? Oh, that shows what the emotions were doing during that last little demonstration. I guess the anger, fear, and happiness are going up and down as it was going in and out of the house, basically. So, suppose we're going to say a bunch more about that video game work later because Lake is going to go over the implementation particular to that to some extent, and for those of you who are interested, try to get you up and running using the Unity 3 game world and the OpenCog system to control the system doing, I guess we have that battery and house behavior working in the new game world now, so you can make it run in and out of its house to get a battery all by yourself, right? So we'll go into the particulars of that, but there's obviously still a lot of work we need to do just in the video game side. I mean, the PLM logic system we're rebuilding. The new video game world is just barely hooked up. The Moses engine has to be re-hooked up as well. So there's a lot of reconnecting existing AI components, which we're kind of in the middle of doing and could use help with, actually. So once all that is done, assuming we get all the parts working together to do stuff in the video game world in a reasonable way, then there's a question like, how far has that brought us toward our real goal of making thinking machines? And I think that ultimately unfortunately, this kind of game world is pretty limited. I mean, I think it's the right kind of thing to be doing because we need some focal task to get all these parts of the AI system to work together. Because the way OpenCog development has been going on so far is mostly like individual people working on individual parts of the system and get the part of the system to do something interesting and make a demo or write a paper or something. There hasn't been a focal task that requires all the parts of the system working together, which is what you need to really hone the whole synergetic interaction between components that is at the conceptual core of the design. And controlling an agent is the right thing. And controlling a robot is really annoying because robots are still really annoying. So we're going to go in the robotics direction, but I think either first or in parallel, getting everything to work together with a game character is a good step. However, you do run into the lack of richness in the game world pretty quickly, and both a lack of perceptual richness and a lack of motoric richness, a lack of richness in the movements that the system can do. Now, there are two ways you could work around that. One way would be to build a much better game world. And that's certainly not impossible. I mean, I put some thought into this a few years ago and tried to design the basis for a much better kind of game engine, where instead of blocks, everything would be made of like very, very small spheres of different kinds, and you define different interactions between those little tiny spheres. And then you could get like fabrics and fluids and peanut butter and all rain. You could get all sorts of interesting stuff, and it wouldn't have to be exactly like real-world physics, right? I mean, it could. What you need is just a richness of many different kinds of material and substance, and then you have to make the AI a body made of a million little tiny balls, so that we could move the different parts of its body. So rather than like an animation pick this up, it would be moving essentially bones and muscles that would move the little balls making up its body. And I mean, you could do that. I mean, that would require a bunch of GPUs to make the thing run. It would be expensive and a lot of programming. The other direction is just go for it and use the AI to control a robot. And for a long time, I was more in favor of just build the next generation of game engines. But the world has kind of pushed us in a different direction because no one is making any headway on building that kind of uber complex game world at all. And it's an expensive, complicated thing to do. Whereas robots are getting better and better because people are putting a lot of money and effort into robots. So we happened to get some funding from the Hong Kong government for using OpenCog to help control David Hanson's little humanoid RoboKind robots. So we're going to be doing some of that, and we're working fairly closely with David and his company Hanson Robotics on that. And quite possibly David is going to move out to Hong Kong in the fall to collaborate closer to full time on this. So yeah, these are the little humanoids looking like that guy.
Doesn't look too good.
Well, yeah. Of course, the human-like face.
Looks a bit scary.
Some people like it. Some people think it looks like Chucky, but I mean, the real point, of course, is perception and movement, right? So I mean, the point is that it can walk around in the real world and has good camera eyes to perceive things with stereo vision. It could pick up this cup. Now it would probably spill it if it was full of water, but it can basically manipulate things. I mean, I think when we get a little further in that project, we're going to get like foam blocks and have it build stuff with lightweight foam blocks it's not going to hurt itself with. But I mean, just in playing with this kind of robots over the last 4 years, they've advanced a lot. Like in 2009 at Xiamen University, when we were playing with the Now robot, I mean, Ray Ting and I made some demos of the Now robot interacting with people, which actually, I'll show you a video of that a little later. And it's kind of cool, but I mean, it couldn't walk very well then. Like, to get that robot to walk, if it was a smooth floor, it would slip and fall. On the other hand, if you put a carpet down, it would have trouble moving its feet forward. So we had to get a wood floor and paint it, so it had the right friction coefficient on the floor for the robot to walk. So it's like okay, we don't want to use a virtual world, we want to use a robot because it's more realistic and can experience the real world, but not actually, right? Because if you have to put it in such an incredibly specialized environment, then what's it really giving you, you know? So they're better now. I mean, just due to advances in what kind of servo motors you can run on a relatively low amount of power. So, and if you look at the Robo Sapien robots built by Mark Tillman in Hong Kong, these walk better than the Now or Robocon, and they're like $50 toys from Toys R Us. Because Tilden has special analog hardware. They're like analog chips with integrating fire neurons, simulations of integrating fire neurons wired into them. And the analog chips are wired together to work with springs in the legs. So for very low power, you can get all this nonlinear dynamics of analog chips interacting with each other. And that's quite interesting. And you can integrate that with a servo motor-based architecture too. So I think robots are becoming less and less bad. And then we have the Kinect now, which is a very cool sensor that can tell you in a close-up environment how far away something is. So it's a lot easier to do depth perception with a Kinect than with stereo vision, for example. Although you can also do it okay with stereo vision. So that I don't think we're yet at the point where every AI programmer should be working with robots, because they're still a pain, and you still spend a lot of time dealing with the robot not working well. I mean, at this exact moment, our Hanson robot is like sitting in the closet in Hong Kong. So, because we're trying to resolve more things in the game world before we go to the robot. But David is going to come out in a few weeks to Hong Kong, and then we'll start more intensively plunging into the AI and robot interactions. Let's see here. Here are some of David's robots, just because they're cool to look at. I mean, we've not hooked OpenCog up to these yet or anything, but we intend to.
Does the little robot also have detailed facial?
Not as many motors as the Robot Einstein, but a fair number, yeah. Yeah, Hanson. Yeah.
You cut off Einstein's head and put him on a robot body.
Yeah, that robot body was the Hugo body built by KAIST, the Korean Institute of Science and Technology, and David built the head, and they kind of glommed them on each other. You see the Wi-Fi antenna on his back, actually.
So, can you say he could pick stuff up? Are his hands actually like opening and closing and stuff, or is it just using both arms?
His hands can open and close. I don't know about this video was made years ago. I don't know about this prototype version, no. Actually, this is an old version. The current faces look a little bit different. I'm not sure if they're better or not. No?
What does he mean when he says it understands you?
I don't know.
Can you tell me a story?
That's Diego's son, who's he built for University of California, San Diego.
He copied his son into a robot.
He's kind of cute, huh? I don't know. How many people think he is cute versus creepy? Who votes for cute? Who votes for creepy? It's about equal. Who votes for both cute and creepy?
The creepiest part is the fact there's nothing from the neck down.
I think I saw this on this BBC Horizon.
Oh, maybe. Yeah.
And then there was another scientist who made a robot.
Take over the world. Jeez, dude. You all got the big questions cooking today.
This is an imitation of the science fiction writer Philip K. Dick.
And I will be good to you. So don't worry. Even if I evolve into Terminator, I'll still be nice to you. I'll keep you warm and safe in my people's
AI stuff happening here.
Watch you for old time's sake.
Not much. The AI that underlies the speaking is mostly like Markov analysis on text. So that's a simulacrum of the writer Philip K. Dick, the science fiction writer, and he wrote a lot, right? So he took his diaries and his books and his letters, and David basically trained a hidden Markov model based on all that writing, and then kind of spliced that into a chat dialogue system he'd built. So it's a hand-built dialogue system where most of the dialogue comes from statistical modeling of the writing of that guy. So I mean, David originally he got a degree in film, and he was a sculptor and animator at Disney. So he's an artist in his basic orientation. So he would view something like this as like a one-off work of art. Like he built it's a sculpture that talks and interacts. And the reason that we have decided to work together is he would like to have more intelligence underlying these things, rather than just having kind of a chatbot with some statistical learning inside it.
Question, are robots' eyes fake eyes or real cameras?
Phil has cameras in his eyes.
But just the location of the eyes or air?
The cameras are in the eyes. Yeah, they're in the eyes. Yeah. Here's another creepy one. Let's see. She'll sing bad music for us. I mean, it's just a demonstration of lip syncing in a robot, basically. Who thinks that's creepy?
He's wobbling. That's why he's wobbling a bit.
I don't know. But she's overwhelmed with emotion. Aren't you? Come on. And me, you fall in love.
Je suis malade, complètement malade.
Actually, I'm kind of sick of her.
Everyone will have seen disembodied head on the desk.
Yeah. Let me see. I'm going to try to, while we're looking at say chatbots, I'm going to try to find the robot chatbot that Ray Ting and I built. Yeah, this was a documentary that someone made about Hugo Degaris and myself trying to make AIs, intelligent robots in Xiamen, China, which ended up with Hugo being fired from his job there. Right? But I just want to find Hugo quitting his job there. Right?
Sorry, you said he got fired?
No, he quit. Right?
Like
Ting is the not. No, I want to find the robot talking. Let's see. No. There's a good conversation with a robot, but I'm not sure where it is.
Actually build fire.
Oh, that may be it. Yeah, so this.
Winning. Becoming the dominant culture this century.
Yeah, this is a now robot. It's kind of similar to the Philip K. Dick system. It was really.
America is not growing, and America is getting fat, and it's getting more and more conservative. I mean, cultures rise and fall, and my feeling is America peaked more or less in the 60s.
I think we'll be done with Hugo's bullshit in a minute.
First step on the moon, that was pretty well the apex.
I mean, his philosophical observation.
Dominance. So I see China very much on the rise, and China seems willing to.
Embodied the first magazine. Yes. Yes, you know what it is? Very intelligent, and maybe that they will be disappointed just by that. But I don't know. We'll see how it goes. Yeah, I think it's here. Yeah. Building a thinking machine will be a difficult engineering problem, but I don't think it's harder than building. Yeah. So this was the now robot, which is an earlier version of the now robot. It's knowing how to make the software. It's understanding how the mind works. Most of the time I've spent during the 20 years since I got my PhD, since I've been working toward creating artificial general intelligence, since I got my PhD. What? Okay, there we go.
I do not understand that.
All right.
I do not understand that.
The self that each of us carries around, the self I have in my mind, the self I have in my mind when I think ignition system. Huh. Okay. So is it Red Ting isn't working now? So you think he's cured in Hanson's robots? I don't know.
This was my favorite part of the film.
What would you like to talk about?
Robots.
I do not understand that. I will become smarter as I grow older.
You are stupid.
I'm smart. How smart is a computer program? And I find the mere suggestion insulting. Do you think your plan will succeed?
I hope my plan will succeed. Stop. That robot. Why did you do that?
Did it surprise you?
A little bit. Are you a robot?
Am I a robot? Maybe.
Am I a robot?
Really?
Am I a robot? You tell me.
I think a lot of people are.
Go back. What do you see? Are you a robot? So you didn't answer, but you see it was supposed to, right?
Interesting. I like to socialize.
Go back. Go forward.
So you have a PC running somewhere which is doing all the
Go where?
OpenCog stuff here. Take it.
How?
Yeah, it's connected to a PC, that's right. Yeah. Yeah, not much happens on board the robot.
Interesting explanation.
Is that Yosha in the back?
Who?
Why?
Yosha Bach?
Yeah. That's Yoshabach, that's right, yeah.
It's
didn't know
all
he was
part
there.
of God's plan.
What is God's plan?
Yeah, that's Yoshabach, who designed that motivational system.
That's the
we're talking
initial
about.
design plan.
What's the final design plan?
This design permitted more complex experiments.
Is our universe an experiment?
This because the universe is all of us is the opening at the center of the universe.
Very interesting. Goodbye for now, robot.
See you later, Ben.
Do that this afternoon, that would be great.
Did the dean end up commenting on that?
No, they didn't understand English. He knows some English now, but so that system kind of like David's Philip K. Dick system. I mean, Ray Ting built much of that chat system together with some other grad students at John University, and I mean, it had multiple sources. One of the sources was just some hand-coded chat rules that were written to give it amusing responses. Now, the weird answers that you say were not hand-coded rules. We didn't encode all that wacky stuff in advance. Like, see you later, Ben was a hand-coded rule, for example. I mean, it knew my name, and then, what's your name, Ben, then see you later, blah, blah. So, and the rest, there was a lot of stuff similar to the Philip K. Dick robot, which was just basically Markovian training. We took a bunch of text from KurzweilAI.net and other future-type sites, and we trained a Markov model on that text to make up sentences based on that text. And then there was some cases it fell back on OpenCog to try to give intelligent answers to things, and it wasn't actually shown in that case, but in some cases it could do things based on visual perception, like what do you see, and tell you what it's seeing. But I mean, the illusion of a semi-intelligent dialogue was pretty much an illusion, and is gotten by combining this basic chat response, which gives you a sense that there's someone having a conversation, the stochastic text analysis, which gives it a lot of things to say, and then little bits and pieces of actual reasoning or perception in there, just to give a feeling of real understanding. And it's really, it's theatrical more than anything else, and it's instructive in how to integrate various sources together to make a kind of coherent dialogue. Now, if the robot had really understood everything it was saying, then that would be extremely impressive. Like, then you'd basically be there at a human level AI, even if some of the stuff it said was nonsense. But it's not the case that the robot understood what it was saying. So, some things, occasionally it does understand something, sometimes it doesn't. Like if you say, what are you looking at? It says a chair. Arguably, you could say it understands that if it learned a model of what is the chair based on seeing a bunch of chairs. But one thing you see, quite apart from the science, from doing all this sort of work, is like having a robot walk up to a person and say, "Hi, I'm a robot," is much more impressive than having like any possible command line or text-based AI demonstration. Like people just like robots, and game characters are not quite there either. They're maybe 20% of the way there, or 10%, because having a robot there in the same world as you seems to be quite emotionally compelling to people, I mean, including to scientists and researchers, not just to the average non-technical person. I mean, it seems like we can't help respond that way to robots. I mean, of course, not everyone is like that, but on the whole, the reaction you get is surprising. I mean, that in itself is not enough reason to work with robots, but it's a sort of bonus anyway. And I think the real reason to work with a robot is if you want a richness of perception and a diversity of actions that you're not going to get from a game world. And right now, I think we need both, and we're pursuing both directions. So we're doing more work in the game world, and in the context of a robot, the main thing we're working on now is visual perception. I mean, just because, I guess for practical reasons, like the robots that we get can walk and turn, and they can do basic picking stuff up and pushing things and so on. But like event recognition, you can't download software for that. So, I mean, to recognize someone walked out of the room, someone got up, just understanding what's happening around it from visual or auditory sensation is effectively an unsolved problem. And there's an academic literature on these things, but it's all basically supervised learning or a closed class of events. So like if you have like 20 kinds of events, like sitting down, standing up, walking, jumping, you can take like 100 examples of each of those, and you can train a support vector machine or some supervised learning algorithm to distinguish those things. But then it's not like open class learning. It's not going to be able to adapt to some new kind of event that occurs, or if say walking turns into two different things because some people walk one way, some people walk a different way. You can't automatically subdivide the classes. Like there is no system that can flexibly recognize the events happening in the world. And that seems like the main obstacle we need to overcome to have OpenCog do useful stuff in a robot, because while action control is important, just having a robot that could walk around, look at people, and take simple objects in its hand and so forth, that's enough to do something anyway. I mean, it's not that able, but it can exist in an indoor environment. And navigation for a robot is not that hard. I mean, we did that. The OpenCog has an internal map, 3D map data structure, like a special structure for a 3D map of its world. And then you can do SLAM mapping and perception and build a map and navigate in it. But I think building a model of what events are happening involving what objects, where and when in the world, that's sort of the bottleneck to being able to have the OpenCog able to treat the physical world as if it was just another game world, basically. Because in theory, any AI we're using in a game world, we should be able to port to the actual physical world without humongous differences. I mean, the physics is different. Like you saw the robot building stairs in the game world, and the way it was doing that would not work in the physical world, right? That staircase would fall down rapidly. So, however, the basic learning process that it used to learn to build that staircase, it could use that to learn to build a staircase using real-world physics. It's not a fundamentally different problem. You just have to build support for the stairs as you're building them. So I think to have the same mind control the video game world, and an agent in the video game world and an agent in the real world, it should be feasible. The main thing we need to get there is good object and event recognition. And toward that end, we've started working with HMR-RL's deep learning vision architecture called Destin, and playing around with connecting that to OpenCog. And so I'll talk about that a little later. But I mean, right now, we're mainly still at the stage of trying to get Destin to work well, just as a vision processing system to recognize objects and events in the world effectively. But we've done some preliminary work, like exporting knowledge from Destin into OpenCog to kind of bridge the gap between the sub-symbolic, like deep learning vision hierarchy and the OpenCog system. All right, so what time does this end, actually?
Well, I'm sure you should have 5. But
Okay. Well, it is almost 5, right? Cool. Yeah, so that's all right. I think so I have talked a lot and I'm kind of exhausted, so I'm ready for someone else to say something. Let's have some comments or discussion or ideas or song and dance routines or whatever.
well, I just find the Robert dialogue part. The Robert talk like a philosopher. I think that maybe we can use the system in that way. Maybe this is somehow ridiculous, but let it to read a lot of philosophical or theological works, and he can pretend to understand that, and he can pretend to produce Plato-like dialogues. That will help students to pass philosophical exams. Well,
that ties in with my idea of making a new religion with a robot as the religious leader. So, yeah, once we've trained the robot all the great books, then it can get humans to follow it. Right? Honestly, I think that you want to start off the robot reading very simple children's books, because the hard part of language understanding to me is connecting language to the world. And philosophy is probably the hardest thing there. The connection between philosophy and the world can be very, very indirect, right? So I think you get there eventually, but I'd be inclined to start with, like, the dog walked out the door, the dog chased the cat climbed up the tree, and wow, what a mean cat, and stuff like that. Yeah, and if you can take that and correlate that with what it sees, that would be impressive. So I think what I want to see is, like, the system just watches what's happening in the world, and it says, well, the man in front of Ben just drank some water, and then it says, the people in the room look tired. I mean, if it could just generate simple verbal descriptions of the salient aspects of its surroundings, to me that would be where we start, because I think all the abstract thinking we've done in philosophy and science, it tends to extrapolate from these very simple everyday things.
Was Fishgram implemented as a mind agent?
I don't think so. I'm not sure. I think when Jade did those particular experiments, I think Jade loaded in a saved atom space and just ran it offline on the saved atom space, and then the intention was there to make it run online, but I think the data structure inside the current version of Fishgram is not suitable to be updated in real time, and will need to be replaced with a better data structure, which is also a good project. Yeah.
It would take then a fair amount of adaptation to experiment with the current game world and Fishgram.
No. Because Fishgram generically works on atoms, right? So to replicate the experiments that Jade did before, what you would do is run OpenCog controlling something in the current game world, save an atom space to a file, and then just run Fishgram to recognize patterns from that file. And in that case, all it is a file of nodes and links, right? It doesn't matter what game world it came from. So that's actually not hard. It's kind of that's the thing with using the atom space as a sort of blackboard for everything. Like once, whatever process it is, once it's put stuff into the atom space, then it's just nodes and links in the standard format. So you don't need that, whether you change the game world or not, doesn't impact PLN or Moses or Fishgram or any of these things. So that wouldn't be hard to do. The work would be to make Fishgram run as a mind agent, the work would be to make it work online, because Fishgram has its own internal representation of the nodes and links, which is suitable for efficient graph mining. But the way Jade built that representation, I think, doesn't play nicely with forgetting or with like incremental building. So, and if you got into doing that, you might end up just replacing Fishgram altogether with some better code that uses the same algorithm, which is quite possible. Right? I mean, I think it's useful as a prototype to see what it could do on those atom spaces. But that's Python code, by the way. You know Python? Yeah, it's easy to read anyway.
Atom space grow exponentially when you add more?
There's a forgetting mechanism. So there's a forgetting mind agent. So I mentioned every node and link has two numbers associated with it, the short-term importance and the long-term importance. Essentially, when the memory starts to get full, the atoms with the lowest long-term importance are kicked out of memory. Now there's also a bit that each atom has, which is the VLTI, or very long-term importance. And that determines whether, if and when that atom is kicked out of memory, is it saved to disk, or is it just deleted into the ether?
But is there a mechanism to bring it back if at some point?
No, there's no like online mind agent. There's no mechanism right now that brings things back, but in principle that should be done. Yeah, I mean in special cases that's been done. Like there's a Postgres database backend, so you can save things to the Postgres DB, and then if you have a query that isn't satisfied within RAM, you can go to the backing store and try to get it. And that has been used within some OpenCog-based language processing applications that Linus Vepstus built, but there's no generic mechanism for that in the system at this moment. But it would certainly be useful. Yeah. But you have to realize that the time difference between loading something from RAM and loading it from disk is like, I don't know, a factor of 10,000 or something, right? So it's like the difference between thinking something and going to the library and reading a book and then coming back with the information. So it's not that it's not useful. In some cases that would be critical, but pretty much when you think about OpenCog's cognition, you want to think about it as what's happening in RAM. Because going to disk is really, really slow, right? Now if you had a robot and it saw someone, it doesn't recognize the person, but it knows the person's name, maybe you could look on disk and then bring up the episode of when I met the guy a year earlier. I mean, I wish I could do that. That's certainly useful. So in some cases like that, it would be quite valuable. But going to disk can't be part of the kind of regular, recurring thought process. Yeah, I mean, and this brings up another thing that still needs to be done. There are two things. Like the OpenCog core system right now does not make really good use of multiple threads. I mean, it uses locking, so a lot of the time many threads are wasted. So some rewriting has to be done inside the core of the atom space in order to let multiple threads use the atom space without wasting time when one has a synchronization lock. And that's not someone claimed to solve that problem last year, but they like forked the code, made new code that claimed to solve the problem, didn't merge it back into the existing code, and didn't give comments on what they did, so it's basically useless. But it took them a few weeks, so that it seems maybe to be a problem that will take a few weeks for someone who's very good at C programming. Then the other harder problem is make good use of distributed processing. I mean, we run it distributed all the time, but basically it's a separate item space on each machine. What you'd like is to have a shared item space around multiple machines. And we went through a long process of like designing how you would do that and convincing ourselves that unfortunately existing distributed graph databases and so on don't work for that. But that's a big implementation task. Implement the distributed item space, but still the API by which cognitive processes access the item space should be about the same as, I mean, you shouldn't need to change the basic API functions. So all these should be like isolated behind that API.
Do you want the PLN inference rules to be represented inside the atom space?
Ultimately, I mean, we debated doing that now and decided not to, just because it's cumbersome and in actual practice the system isn't going to do anything with them. So right now, the PLN inference rules, in the new version of PLN that Raman is working on, they are Python code. But I mean, he asked me about it like 2 weeks ago. I mean, you could perfectly well put them in the atom space. It's just would make debugging slower and wouldn't really add anything in the immediate term, because basically we need to make PLN solve easier problems before we set it to learning new inference rules, right? So I guess when we have a smart enough system to learn new inference rules based on experience, changing PLN to have those rules be in the atom space is like a couple of days' work. It's not going to be a big deal, right? Whereas having the natural language grammar rules in the atom space would be useful now, because adapting those based on experience is a much easier thing. As you see new language, you could update the probabilities of the different grammar rules and so on. It's a less abstract level of knowledge. Right?
You were talking about some self-programming during the lecture, but it isn't clear for me what kind of state it is now in OpenCog.
Well, that system is not doing self-programming now.
And what is your plan for it?
I think that serious self-programming comes fairly late in the development of a human-like AGI system. Like I think we could get to a virtual toddler that's like a 4-year-old child or something without any self-programming happening. I mean, ultimately, once you're getting toward the adult level human AGI, that'd be great to have the system, say, improve its inference rules, as Cosmo was alluding to, but...
Basically, we're talking about reflexive.
Yeah.
Is it? So, system should be grown up to be reflexive.
Well, there's multiple kinds of reflexivity, though. I mean, for example, I am not able to modify my neural architecture. Like I can't expand the size of my hippocampus, right? I can't add a bunch of new connections between the thalamus and part of the cortex. I mean, there's certainly a lot of ways, but there's a certain level below which the human mind is actually not very reflexive, right? And then there's a certain level on which it is reflexive. And ultimately, for an AI, it could be totally reflexive, right? I mean, ultimately, a human could be too. Once we have strong nanotech, it can rewire our brains. But an AI could do it more easily because it's all just computer code. So the question with something like OpenCog is, where do you draw the line? Like, where is the reflexiveness that you need to get to human level AI versus where is the reflexiveness that you only need when you want like an Uber system that can rewrite all of its own thought processes. Now, my intuition is that it's okay to like code PLN logic, code the Moses program learning algorithm, code the basic math for spreading importance around among the nodes and links. And I think those things can be, as human programmers have decided them, and don't need to be self-modified by the system to get to a human level AI, just as I don't modify the way my dopamine receptors work or the way neurotransmitters spread in general around my brain. I mean, there's adaptation in the brain. Like if I lose an arm, then my brain will adapt eventually to not map where the arm was. I don't have a phantom limb for a while, but eventually it will adapt. But yet, I don't reflexively control that process. I mean, that's the kind of unconscious adaptation. If I did reflexively control it, then people could get rid of a phantom limb just by thinking, no, damn it, I don't have an arm more. Stop making me feel like I do. So my thought is that the atom space, of course, is constantly rewritten by the system. And a lot of control heuristics can be put into the atom space. So, say decisions for what to reason about when, or what parameters to choose for Moses in what context, or like, do you do deductive reasoning now, or do you do inductive reasoning now, or do you not reason at all? Right? Do you just try to gain more experience? That sort of thing, I think, has to be in the atom space as cognitive content that can be revised. Whereas I don't think the system needs to reflect onto to modify the PLN logic rules or the way Moses crosses over program trees. Eventually it does, but I don't think you need that to get to human level AI. And that is different than, say, Kristen Thorson's approach, where they want to sort of have the system reflect on everything it does and kind of have complete transparency into all of its operations and be able to modify everything by learning. I mean, I think that is possible, but I think that's a much, much harder problem that would take many, many orders of magnitude more time and resources to get it to work. Whereas if you are clever enough to come up with the right base set of learning mechanisms, then I think you could get that set of learning mechanisms to get you to human level AI. Because the thing is that to learn your own learning algorithms just requires a hell of a lot of data and experience. I mean, you just need so much data of the system learning in different contexts with different parameters for the algorithm in different ways. And I think that's more data and experience than a person has, certainly, or than AI is going to get very, very, very quickly. Because basically the more abstract your learning gets, the more data you need to feed the learning engine. And if you're learning how to achieve goals in the world, but not learning the basic learning algorithm, you need many orders of magnitude less data. Anyway, that's my thinking. But on the other hand, the OpenCog framework could certainly be used for a totally reflection-oriented architecture. Like you could, I built a long time ago, I built a simple version of PLN basically in the atom space, in combo, in the set of nodes and links that are used by Moses. So we implemented PLN in atoms. So then, in theory, you can have that version of PLN learn to improve itself, since that version of PLN was all cognitive content. Now, in practice, that version of PLN was not smart enough to solve problems of remotely that order of complexity, so it didn't really help. But on the other hand, you could take an approach of make a simpler learning algorithm, implement the simple learning algorithm as schema nodes and execution links and predicate nodes and stuff in the atom space. Try to have that simpler learning algorithm learn to improve itself by rewriting the atom space, and have it take off from there. I mean, there's no reason the OpenCog framework is ill-suited for that kind of project. That would be fine. I mean, we have a programming language interpreter, we have a knowledge base, you can forget things. That would be quite interesting. I guess I made the intuitive judgment. I think that's probably not the shortest path to get to human level AI, so it's not what I'm doing, but the framework could certainly be used for it. I mean, if I had a massive amount of money, I would pay a team to work on that because it's cool and might yield something. So.
Have you had some demonstrations of PLN helping Moses?
No.
Is that an idea?
It should be done, yeah. I mean, it would be easy, but actually, I mean, it would be... The context in which I wanted to experiment with that, actually, and this is something that's been on the back burner for so long, we've been using Moses to analyze genetics data from different organisms. So let's say flies and humans. And it is a specific case we've been looking at because we have data from long-lived flies and long-lived humans. Like these flies live 4 times as long as normal flies. And also from centenarian humans. So, I mean, there are homologs between fly genes and human genes, right? So there's a mapping between fly genes and human genes. And there are very broad mappings between like pathways and processes in the different organisms. Like here's the apoptosis pathway, pre-programmed cell death pathway in flies. Here's the apoptosis pathway in humans. But there's a whole region in between pathways and genes where there are homologies between different organisms that aren't explored. So I thought if you took the Moses classification rules used to distinguish long-lived flies from short-lived flies, and then try to use PLN to find the analogies to that among human genes, right? Then you're using PLN, like uncertain analogy mapping, to find the analog of a pattern in fly data within human data. Then you can evaluate and see is that pattern actually there in the human data. So that's one example that we have an immediate, it's not that AGI-ish, but we have an immediate practical benefit. And we have like files of good Moses classification rules and data sets there. So that would be doable. I mean, similarly, when we were using Moses in the game world, which I'll talk about a bit tomorrow. I mean, if you use Moses to say, what were we using Moses? Moses learned to play fetch, for example. So Moses learned the game where you throw a stick, then the agent, which is a dog, the AI-controlled agent would run and get the stick and bring it back. So, yeah, what you'd like is, if Moses learned to play fetch, and then you want to teach it to play tag. Tag being the game where you run around and try to touch someone else, right? I guess they must have that game in China too, with a different name, right? So if it had learned to play fetch, could then PLN kind of extrapolate how to play tag from that? Or if it learned to play tag, would it learn to play hide and seek, right? Because most of the skills are the same, there's just a little tweak there. So in those cases, you take the program learned by Moses and try to get PLN to generalize it. And yeah, that would be natural enough to do because you can take a Moses learned model, we've exported those into the AM space, and then PLN can reason on those, but it just, no one got to it. Huh?
Nils talked about it at a former summer school.
Yeah, well, but Nil has been working with me on the hedge fund for the last year and a half, so, which has resulted in some improvements to Moses being, much of the hedge fund stuff, of course, is proprietary, but some of the hedge fund stuff has resulted in improvements to Moses that have got pushed back into the main Moses code base. So that's been valuable, but hopefully the hedge fund will cause Nil and me and Cassio to make massive amounts of money, and then we can fund a huge OpenCog team and get to a thinking machine faster. But in the meantime, it is distracting Nil from doing that sort of thing in OpenCog. Mm-hmm.
bioliterally, you can use it to extract like knowledge, discover knowledge from
We did.
abstract.
Yeah, we haven't used that in like 5 or 6 years. So I'm sure there's better ways to do that now. That's kind of dead code. Yeah. Yeah, that was interesting. That was using the relic system that Ray Tane will talk about tomorrow, I guess. So that was basically that was the relics information extraction system connected to some other open source code for entity extraction in the biology domain. So we took some entity extractors and some specialized biology relationship extractors which existed at that time and hacked those together with relics to recognize relationships from PubMed abstracts. But by now, BioNLP has advanced a lot, and there's other systems that work better than that thing did then. It would be interesting to build something new for that, which could be done, but that's a pain, though. I mean, doing the BioNLP is like a whole pain unto itself, because, I mean, there's so many different confusing names of everything, and biologists are such horrible writers. Right?
But do you think with this, you can potentially build an expert system, for example, from the knowledge you discovered?
Yeah, I mean, I know people who are interested in having a longevity expert system built that way. Right? So, yeah, of course that could be done, but I mean, the thing is there's a lot of biology databases already, right? So most of the simple information you would find in the abstracts or papers is already in some existing biology database. So then you could just, if you wanted to make a question answering system like that, you could just take all the existing biology databases, feed them into the atom space, and then do question answering that way without having to get it out of the text. Now, after a certain level, there's stuff that isn't in the databases and you need to get out of text. But then you're definitely beyond what you would call an expert system, I think, because the simple knowledge is already in databases, because biologists are pretty good about putting things in databases. Right? But yeah, I know, of course, there's a lot of interest in that area from biologists, and the business models in that area are so bad that almost no one wants to do it because there's no way to make money doing it. I mean, like within our hedge fund, we're doing a similar thing in finance. We're extracting relations from financial news articles to understand what events happen between companies. And that's similar. I mean, you do domain-specific engineering for financial news. But people with money have a motivation to pay for that to be done, right? Whereas in the biology domain, the business model is a lot dodgier, right? So it's hard. I mean, if you make that expert system, who will use it? I mean, you can put it for free on the web, that's cool, but you're not going to make much ad revenue. Will doctors want to use it? Of course not. It threatens to put them out of their job, right? So it becomes dodgy, and that's... overall, I found bioinformatics is a fascinating and important area in which it's almost impossible to make money. If I'm going to work on something that is really cool and doesn't make any money, we might as well just work on AGI. But of course, in either case, once you get to a certain level of maturity, then you can make an insane amount of money, or if you're more oriented toward research than money like me, you can make a moderate amount of money and spare a hell of a lot of awesome research, right? Once you get to a certain level of demonstrated functionality, which unfortunately we're not at this moment.
But I think it's easy to combine AGI ideas with military purpose than to sell it to
I don't want to.
You don't want to?
No. I am opposed to needless killing of people. And I mean, apart from my own personal taste, I feel like on the whole, that'll be a bad way for the first AGIs to be unveiled on the planet. I mean, we've seen that in science fiction movies a lot, but I mean, it would be nice if the first human ever lives were not killer robots, right? I mean, the other thing is, beyond issues of ethics or personal taste, I mean, early stage AGIs are going to be unpredictable and not that smart and make a lot of mistakes. And I think when you do military contracts, and I mean, I lived in Washington, D.C. for 9 years, so I actually did a bunch of work for military and intelligence agencies, although I stayed away from anything to do with actually killing people in any direct sense. But, I mean, you need stuff that's very reliable there, right? And you need stuff where what the system did is auditable. I mean, these guys want to see why a decision was made in detail, and they definitely don't want to do something different from doctrine. So these actually are not properties that, say, 3-year-old kids tend to have, right? They can't explain why they did. You can't explain why they did what they did. And they're different from the doctrine you told them all the time. So it might be that the requirements for kind of auditability and reliability in the military domain actually would make it difficult as a testing ground for early stage AGI. Unless you have some crazy dictator who just wants to put giant robot toddlers out in the battlefield fighting for his country. It might happen, but that's not any of the major military powers, fortunately. But I mean, I wouldn't rule out. I mean, there are people in the military of the U.S. and other countries that love technology. Probably 70-80% of all AI funding in history has probably been from the U.S. military. So that's it. My cell phone's about to explode. No. Nothing important. Yeah, I mean, I think that may be the way it happens, but I would prefer to get funding from other sources not involved with killing people if possible. I mean, Google is now funding a lot of AI. They're not funding AGI particularly, but that is encouraging that there are sources of, there is money in the world being spent on AI from non-military sources, and the Hanson robots and the Mark Tilden Robo-Sapien robots, again, there's a possibility there of toy robots. I mean, if you could make a robot for like $50 or $100 US with Wi-Fi connecting to an AGI brain in the cloud, I think that's an interesting business model that many people could find appealing. I mean, you'd have to do the design of the character and the body right and all the marketing right and so forth. But the price point for fairly able little humanoid form factor robots is low enough now that you might be able to make that work. I mean, when it was the IBO for a couple $1,000s, of course no one wants to pay that much. Right? And video games as well. I mean, right now we're still in the early stage with that, but I think once the game AI can actually do cool stuff in the game world, there's no reason you couldn't have a blockbuster game with an AI that learns and reasons as a central aspect of it. So of course, what I saw when I worked with the military community is that they get most of their ideas from games and movies anyway. So once you put it in the video game world, then it may end up wafting its way into that world. But then hopefully we'll be even more advanced in the non-military domain by then.
Lightsabers.
Yeah, well, that's just amazing. Like I remember some general in the army at some point. This is maybe 2003, 2004. He saw the movie Hackers, which is a not particularly great movie, but it involves these people like navigating a database which is structured like a virtual city. So like you zoom through the database, and each item of data is represented by some big building. And so he saw this, like, yeah, that's great, build me that. All of a sudden, like, X million dollars are allocated to some subcontractor company to build that user interface for the general to use. And everyone working on it knew it's a really dumb idea. Like, yeah, it looks good in a demo, but actually it doesn't make any sense as a way to navigate data. That was built, that was delivered to the guy, you know? And, I mean, you see it over and over and over again. Because, I mean, these guys don't necessarily have that many innovative ideas of their own, because that's not such a culture of innovation, but they see many cool ideas in the movies. I don't know if that's a U.S. specific thing or not. So yeah, if you want to get a very cool technology funded with a lot of money, get someone to make a Hollywood movie with that technology in it.
There's one coming out soon, isn't there, with about AGI stuff?
Oh, there's Transcendence is coming out with the mind uploading. Yeah, I mean, I think that's good, actually, since most politicians and decision makers aren't going to read and think about technology, but they'll probably go out and see movies. So if this stuff gets into movies, maybe that's how it will ultimately impact the people making the resource allocation decisions. We need some AGI movie to outdo Terminator, right? Because now, every time you talk about AGI, people are like, well, isn't that just going to like get naked, come back in time and kill us all, right? So, and
it's like, nah, there's no time travel.
Yeah, so, I mean, but that has been an archetypal image in people's minds. So if there can be something on the positive side that would counteract that would be a good thing. Right? Of course, it's easier to arouse people's fear than any other emotion, probably. So there's a tall order there. Right? All right. Well, so we will reconvene tomorrow. However, as I don't like getting up early, let's do 9 instead of 8:30. Right?